Okay, in the last few videos on the playlist that deals with solution redox reactions, we learned how to balance those reactions. And now what we're going to do is I would like to teach you about the classic permanganate laboratory. And this is a lab that happens in most general chemistry classes at the college level, and it's one of the classic labs that occurs in the advanced placement chemistry classes. And basically, this laboratory capitalizes on the solution redox reaction between permanganate, which is a strong oxidizing agent. We call it a strong oxidizing agent because it is a compound that is easily reduced. In this case, we're going to look at this from the point of view of the laboratory that deals with the reaction of permanganate and iron plus 2. All right, and this is the balanced net ionic equation for this reaction, which I demonstrated in a previous video. And what I'm going to do here is just write the equation down at the top of the screen, and we're going to now utilize this reaction and this equation from a practical point of view. All right, so here's the balanced net ionic equation. Now, one of the main practical uses of this type of chemistry is in the quantitation of unknown substances. And in this case, what we're going to be doing is we're going to utilize the permanganate ion to quantitate an unknown solution of iron 2. Now, this is a process that requires essentially two steps. In the first step, we need to determine the analytical concentration of the permanganate solution. All right, and we're going to be using a solution that's going to be approximately 0.02 molar, and I'm going to leave these two decimal places as unknown. All right, so in the laboratory, I would dissolve enough potassium permanganate in water to produce a 0.02 molar solution. And in the first step of these kinds of laboratories, the student will confront what the teacher is going to call a standardization. And in that standardization, what you have to do is determine the concentration of permanganate to 4 decimal places so that we actually have an analytical concentration of this. And in order to do that, we're going to start with a known concentration of the iron 2 cation, and where we're going to get the cation from is going to be a 0.5 gram, and this is going to be masked out analytically so that we're going to know this value to 4 decimal places, and specifically we're going to use the compound which is iron sulfate, iron 2 sulfate, heptahydrate. All right, this is a green solid, green ionic solid, comes in a bottle. Its molar, well, I'll get to its molar mass in a little bit. So we're going to be using a 0.5, and then we're going to know this mass to 4 decimal places. So I'll write it like this. And it's the iron 2 sulfate heptahydrate. All right, now, in any sort of quantitative lab where we're using solutions and where we have at least 2 reactants that are involved in the reaction, we're going to use a technique that's called titration, and I'm going to define that down here. Now, what the student needs to realize about this is that the word titration is specifically regarding a process that involves many different kinds of chemical reactions. And all right, so let me give you the definition. The definition is the incremental addition of one reactant into another reactant. All right, incremental addition of one reactant into another reactant. Or another way of looking at it, the incremental addition of one reactant in a reaction with another prescribed amount. So coming back to what we're doing here, we're going to have a predefined amount of iron 2 sulfate heptahydrate. So this is a known quantity. We're using a simple calculation, we'll be able to determine how many moles of this reactant are going to react with the permanganate. The molar mass of this, just so that we have it here, is 278.31, and that's grams per mole. All right, and in a titration, and I've imported a couple images here off of the internet. In a titration, the important thing for the student to realize is that you're going to have the two main reactants physically separated from one another. And with one of the reactants, you're going to need a method that will allow you to incrementally add that reactant into the other reactant. So in this case, what we're going to do is we're going to have the iron compound down here in the collection flask. So my iron 2 sulfate will be here in the collection flask. All right, we'll just do it this way. And the permanganate solution of unknown molarity, unknown analytical molarity, is going to be up here in this glass cylinder we call a burette. And notice that the glass cylinder has milliliter graduations on it, and near the base of it, it has what we call a stopcock. And basically, the stopcock is a valve that allows you to turn the burette on or off, so you can dispense material incrementally from the burette into the collection flask. And so we've essentially met two criteria. We have the two reactants physically separated from one another, and we have a method utilizing this valve to add systematically and incrementally little bits of the permanganate solution at a time, so we can control how much of the permanganate is reacting. And after the reaction is over, then we're going to know precisely the volume of the permanganate that was dispensed to reach the end of the reaction. All right, now permanganate is a colored solution. All right, it's dark purple, and so I'm going to indicate that here by just giving the burette some coloration. So the permanganate solution is going to be in the burette. All right, and the iron sulfate heptahydrate solution is actually colorless, and I imported this other image here so you can see what the color of the iron 2 solution looks like. So the iron 2 solution is colorless to start with, so this is FeSO4.7H2O. So in the beginning of the experiment, all right, the iron 2 solution is a colorless solution. It will be located here in the collection flask. All right, now there's another part of this that we need to talk about, because notice in the net ionic equation that we have also the requirement of 8 H pluses. So we're going to need to set a situation up here so that the only thing that matters in terms of the chemical reaction is going to be the permanganate that's in the burette and the iron 2 cation, which is here in the collection flask. And we need to handle the acidity here in such a way that we make this into an excess. All right, and the way that we're going to do that, so we're establishing the acid as an excess. The way that we're going to do that is when we prepare the collection flask. All right, we're going to mass out our 0.5 grams of the iron material. All right, and we're going to dissolve it in, and different professors and different teachers are going to do this different ways. But in my class, what I do is I have the students dissolve this material in 20 milliliters of 1 molar sulfuric acid. All right, and normally if the student is careful about this and they make sure not to shortcut this step, then the sulfuric acid, which is providing the hydrogen ions here, the H pluses, provides enough of that material so that the H plus is in excess. So what the student's going to do to set up this reaction is they're going to carefully weigh out on an analytical scale a 0.5 gram of the iron 2 sulfate. They're going to do that to 4 decimal places here, so they're going to know the mass very precisely. All right, and that's going to be analytically transferred into the collection flask. So when the student transfers this mass into the collection flask, shown here in the titration underneath the burette, they're going to need to make sure to carefully rinse the grains of that salt into the collection flask, and I usually have my students do that directly with the sulfuric acid, and then they eyeball the volume up to approximately 20 mils. Usually on these Erlenmeyer flasks, the first graduation that appears on the flask is at the 50 mil level, and so you can very easily eyeball in the volume of this that you need by just making sure that you've added enough sulfuric acid so you're a little bit over halfway up to that 50 mil mark. So you rinse in the 0.5 gram of the iron 2 sulfate using the sulfuric acid, and then you wash down the sidewalls of the Erlenmeyer flask, of the collection flask, with the sulfuric acid solution, and then eyeball the volume so that it's a little bit over halfway up to the 50 mil mark on the graduated, or excuse me, on the collection flask, the Erlenmeyer flask, and you should be good to go. Now, what's going to happen is you're going to start to add the permanganate solution into the solution that contains the iron 2 sulfate. And initially, when the permanganate drips down into this colorless solution, the permanganate ion reacts immediately with the iron 2. And literally, the permanganate ion is broken apart. See, if you look over here on the product side of the reaction, you see that we're producing Mn+2. So this reaction produces a colorless solution in the beginning, all right? And as you progress, as you let out more and more of the permanganate solution into the iron 2 sulfur, into the iron 2 sulfate solution, you see that we're also producing iron 3. So over the course of the reaction, this reaction is the reaction flask or the collection flask solution is going to begin to take on a yellowish hue to it, a light yellowish hue, and that's because of the presence of the iron 3 cation. All right, now we need to know how it is we know that we're at the end of the reaction, because what we're going to need to be able to do here is establish the volume of MnO4 that's dispensed into the iron 2 sulfate solution to reach the point at which all of the iron 2 that we put in the reaction flask has reacted. So there's 2 concepts here we need to describe. The first one I'm going to describe is called the equivalence point. All right, now the equivalence point is literally the point at which the two reactants have completely reacted with one another. All right, and I'm going to define this in exactly the way that we're using it here. So the equivalence point in this case is the point where all 0.5 grams of the iron compound is reacted. All right, so there's no iron 2 sulfate, there's no iron 2 left in the collection flask at the equivalence point. All right, now at the equivalence point, the only thing left in solution, so I'm going to write that down here. So at equivalence, I'm going to abbreviate equivalence. The only thing in the reaction vessel, in the collection flask, is going to be iron 3, Mn plus 2, and the H2O that's produced in the reaction, which is irrelevant because the reaction is being carried out in water in the first place. All right, so at the equivalence, this is the only thing that's left. Now, if you're doing this experiment correctly, literally at the equivalence, this burette should be shut down, because as you get closer to the actual place where you reach the equivalence, what you're going to notice is that for each drip of permanganate you put in here, the pink color that's shown here on the right, which I'm going to address in a second, will be flashing through this solution and holding its coloration for longer and longer periods of time. And at the point where you see that start to happen, the smart chemist is going to shut this burette down. And what you're going to do is you're going to start washing in using distilled water. You're going to start washing in fractions of drops. And what you're trying to walk towards is the coloration that we see here on the right, where we see that we have a pink solution. All right, this is what we call the end point. The end point. Now, the end point, I want to be very clear about this. The end point is not the equivalence. It's not the equivalence, because here's what's happened. We have reached the point in the equivalence already where all of the iron 2 has completely reacted, and we still have a colorless solution at that point, noting that the only thing that's in there is going to be iron 3, Mn plus 2, and water. This solution is going to have a slight yellowish tint to it, but it's going to be impossible for you at that point to tell with the naked eye that the reaction is actually over. It's not until you wash in that next fraction of drop that you actually hit the end point. And what the end point represents is, it represents, and I'm going to write this down here, it represents a slight excess of the MnO4 minus anion, whose color is pink. That's when you know the reaction is over. So technically speaking, once we reach this pink color, which is the end point, and we stop the reaction, you actually have walked past the equivalence point by a slight amount. Usually you're past the equivalence by a fraction of a drop, but it's safe to say that it's usually about 1 drop. All right, and you're going to need to know the volume of 1 drop, because what we're after here is the volume of the permanganate required to actually get to the equivalence point. That's going to be the important aspect of this. So whatever volume we get on the burette, you're going to want to be able to subtract the volume of 1 drop that got us to the endpoint, because the endpoint is actually a slight step past where the equivalence is. Alright, now in the next video what we're going to do is I'm going to show you how to do the calculation to actually find the concentration of the permanganate solution.